In this podcast, we'll start by looking at Newton's laws. Before Isaac Newton came along, many people believed that the important distinction in kinematics was between systems that were moving and not moving. Isaac Newton realized that the important distinction was between accelerating and non-accelerating reference frames. Each of the three laws describes this distinction in a different way. Newton's first law. Newton's first law is about inertia, and it says this: an object in motion remains in motion. But I'm going to pause here and add some words of my own. What Newton meant was not just an object in motion. He meant an object in motion at a constant velocity. Remains in motion. And an object at rest remains at rest. Unless acted upon by an unbalanced force. What we would call a net force. So here, notice what he's doing is he's lumping together constant velocity and at rest as similar situations. For both objects moving at constant velocity and objects at rest, the net force is 0. That means all the forces balance out. Let's take a look at Newton's second law. Newton's second law is a description of what happens when we apply a net force to an object. And essentially, Newton's law says that net force equals mass times acceleration. A reminder that in this class, F stands for force, and it's measured in newtons. M stands for mass, and it's measured in kilograms. And A stands for acceleration, and it's measured in meters per second squared. This is a pretty simple formula, but it's a very powerful one because it describes the acceleration that occurs when a net force is applied to an object of a given mass. Let's take a look at Newton's third law. Newton's third law is often described as the action-reaction law. For every action, there is an equal and opposite reaction. But again, that language isn't quite what Newton meant. What he really means is, for every force, there is an equal and opposite force. And this only works for objects that are not accelerating relative to each other. So let's take a look at a very simple example and then a more complicated one. We've looked at the situation of book on table quite extensively at this point. We've got a force of gravity and a normal force, and this is called a force pair. You've got the book pushing down on the table, that's gravity. You've got the table pushing back up on the book, that's the normal force. Those are your equal and opposite forces. But let's suppose for a minute that we have a person pulling a wagon. And let's say that the person is accelerating. Maybe they are at a stop and then they decide to jog with the wagon. Now, the wagon and the person are not accelerating relative to each other. They are accelerating relative to the ground. So, if I look at the force that the person exerts on the wagon, an applied force of the person on the wagon, that force would be equal and opposite to the applied force of the wagon on the person. So here I've got person on wagon, and it makes a force pair with the wagon pulling back on the person. Those two forces are equal and opposite. Now, in order for the whole system to accelerate forward, the person's feet must exert a force on the ground that is bigger than the applied force pulling back on the person. So the person has to have shoes that have enough friction that allow them to push the person forward with more force than the applied force of the wagon on the person.